Now we are going to implement a quadrilateral thick plate element. And for that, I'll be using the bilinear shape functions. Now for the thick plates, we need C0 continuity, so we can definitely use the bilinear shape functions for that. So my coordinate interpolation will be again by using bilinear shape functions ni, xi. My displacement field, so we have only transverse displacement here, will be equal to W, and it will be again interpolated using bilinear shape functions. And also we need to define the rotation field. So theta I, or let me write it this way, theta x is equal to, I is equal to 1 to 4 ni theta xi, and theta y is equal to, I is equal to 1 to 4 ni theta y I. Okay, so we are using the bilinear shape functions for all the interpolations. Now the bending deformation. So our curvature definition is as follows. Del theta y over del x minus del theta x over del y, del theta y over del y minus del theta x over del x. This is our curvature, and I want to obtain the curvatures by multiplying with the B matrix for bending times the nodal displacements. And the nodal displacements will have the following form. We have the transverse displacement, rotation in x, rotation in y, and we will write it for the 4 nodes. So combining these two, you can write it this way, curvatures are equal to, so I'm using these interpolation functions. So there is no relationship with the transverse displacement. The first column will be all 0. The first row, second column, 0, and I got del theta y over del x. Then I have del n1 over del x here. So it will continue, and at the end I got 0, 0, del n4 over del x. And this one is for node 4. Okay. The second row I will be using this. Then this is equal to minus del n1 over del y. This is 0, 0 minus del n4 over del y, 0. And the shear strain is the combination of these two. So this one, del n1 over del x, this has to be minus, and del n1 over del y, 0 minus del n4 del x del n4 del y multiplied by the nodal displacements. And this will be my B matrix for bending. Now let's take a look at the shear deformation. The shear strains are defined as follows: theta y plus del w over del x, theta x minus del w over del y. This is the place where we relate the transverse displacements with the rotations. Again, we say that shear strain is equal to B matrix for shear multiplied by the nodal displacements. In that case, let's write it this way: shear strain is equal to, so I have del w over del x. Again, we have the following interpolation for the transverse displacement. So I should write del n1 over del x, nothing with theta x, and n1 for theta y. The second row minus del n1 over del y. I got theta x here, n1 and 0. And for the fourth node, I'll just write that n4 over del x is 0 and 4 minus del n4 del y n4 and 0 multiplied with the nodal displacements. And this matrix is the BS, is the B matrix for shear, strain displacement relationship. Now let's take a look at the total potential energy function one more time. For the internal strain energy, we have written the following: 1 over 2 integral over the area, curvature transpose multiplied by the material matrix for bending multiplied by the curvature and integrated over the area, plus the second term is for shear area, shear strain multiplied by the material matrix for shear multiplied by the shear strain itself integrated over the area. So let's put these two, this one and this equation, into that equation. In that case, I have will be equal to 1 over 2 area U transpose B for bending, D for B, B for bending times U dA plus 1 over 2 U transpose BS transpose DS multiplied by BS U dA. And from this expression, it's very typical, so we know that if I evaluate that integral, that will give me the stiffness matrix for bending deformation, and if I integrate that expression, that will give me the stiffness matrix for shear deformation. So the stiffness matrix can be evaluated as follows. A BS DS BS DA, and K for the thick plate is nothing but the summation of bending stiffness plus the shear stiffness. Of course, in order to avoid locking, we will be using reduced integration to evaluate Ks. Now let's take a look at the implementation of the quadrilateral thick plate element. Now here we will be using the bilinear shape functions. So these are the derivatives of it. This is the combination of the derivatives of the bilinear shape functions. And since we interpolate the coordinates again by using the bilinear shape functions, the Jacobian calculation is based on these functions. Now we have the shape function derivative, so I'm just calculating the derivative with respect to psi with the Jacobian inverse, derivative with respect to nu with the corresponding Jacobian inverse, and here I'm directly obtaining the derivatives with respect to the Cartesian coordinate system. So this would simplify my upcoming codes. Now, as we discussed, we have two different B matrices strain displacement relationship. One of them is for bending deformation, the other one is for the shear deformation. This is the strain displacement relationship, so I'm just locating the derivative here in its place at the B matrix, negative derivative with respect to y, and put this one here, put this one here. This is what these two rows are doing. So this way I'm fully generating the B matrix for the bending deformations, the same for the shear deformations. If the second row, put this one, first row, put this one, and the values of the shape functions itself. And this is this algorithm will gives the strain displacement relationship for the shear strains. Now we have the moment curvature relationship, and this is the shear force shear strain relationship. So I put 5/6 in front of it, so this will allow the shear correction in the bending area. Now the stiffness matrix calculations. So here I'm using 2x2 integration. The procedure is the same. We end up with 12x12 stiffness matrix. Calculate the B matrix and do the numerical integration and obtain the stiffness matrix. This calculation will give the stiffness matrix for the bending deformation. Now for the shear deformation, as we discussed, I'm using a single point integration, which is at the center of the element. Calculate the B matrix for the shear and obtain the shear stiffness matrix, and this is the shear stiffness matrix. Now the rest of the equations are the same. I'm just assigning equation numbers to every degrees of freedom, calculating the force vector. Now the global stiffness matrix, the only difference here is I'm just calculating two different stiffness matrices, one from the bending, the other one from the shear, adding them up and put it in the global stiffness matrix. And this is the classical procedure for the displacement calculation. Now the element force calculation I'm doing a little bit different here. In the previous elements I was directly calculating the stresses at the nodes, but here I'm changing it. So remember that this is our element, so we are calculating here I'm calculating the stiffness matrix at the centers, at the Gauss points. And what I do again, by using the bilinear shape function, I am extrapolating them to the nodes. Okay, so in order to do that, what I do is very simple. I'm just saying that, okay, if this is my original element and if this is -1 and 1, -1, let's say. This is not, but we are just assuming that it is. So, and I know the stresses at these 4 points. What would be the stresses at these corner nodes? So in order to calculate that by using the bilinear shape functions, I need their coordinates. So I'm just scaling it. This is the original coordinate of this one is -1/√3 and -1/√3. In order to make it equal to 1, I'm just multiplied it with the √3. Then these corner nodes, the coordinates of these corner nodes will be -√3 and -√3. So basically this extrapolation function takes 4 stress points, calculated at the Gauss points, use the bilinear shape functions by inputting these numbers, and get the contribution of each stress to this point, add them up, and you'll obtain your extrapolated stresses, moments, or forces at the exterior at these nodes. Okay, so this is another way of calculating the stresses by just extrapolating the stresses from the Gauss point. Which one is better depends on the element. Sometimes it doesn't matter. Sometimes this approach will give a better result because we obtain stresses. I mean, the most accurate stresses are obtained at the Gauss points. So the element force calculations here, calculating the moments at the Gauss points. So these are the coordinates of the Gauss points, and I'm just extrapolating them. Shear, I'm just calculating it at the center. Now come our example problem. So the delta that we are looking for should be equal to 0.024 with the shear deformations. The stress, or this element won't give us stress, but it will give us moment. So moment is very straightforward, is 20 by 4 should be 80 kilonewton meters, and the shear force here should be equal to 20 kilonewtons. So since I'm modeling this cantilever, this will be my model with the plate element. So this distance will be the width, which is equal to 0.4, and the thickness will be the depth of the element, that's 0.6. So this is node 1, node 2, node 3, and node 4, and this is the coordinate matrix. So I'm just fully fixed. That's why all the rotations and the translations at this node are fixed. So I'm just applying 2-point loads here, 10 and 10, in the transverse direction. This represents that. The width is 0.4 and the depth, the thickness of the plate is 0.6. And when we do the calculations, since I did the single point numerical integration, as you see, I didn't observe any shear locking, and the displacement that I get with a single element is 0.0018, which is acceptable for a single element solution. When we look at the internal forces, now the moment that I see here is around 100 kilonewton meter per unit meter, right? We can just assume that it's constant. So if I multiply it with the with the width of the member by 0.4, this gives me a moment as equal to 40 kilonewton meters, which we can say that that's not a good approximation in terms of moments. Now, the shear force is 50. Again, this is 50 kilonewton per unit width, which is meters. So I have to multiply it by 0.4. That will give me 20 kilonewton shear force, which is equal to the applied load. So the shear forces are okay. Now let's improve the result. I'm now using 5-element solution. These are the coordinates, nothing changes, and the tip displacement now becomes equal to 0.00237. So which is a much closer result to the beam theory. But let's take a look at the moments. Now the moments are in a much better shape, right? So we can just say that this is something like 180 kilonewton meter per meter multiplied by 0.4. That will give me a moment that's equal to 72 kilonewton meters. And shear are 50 multiplied by 0.4, and that gives me a moment that's equal to, shear force that's equal to 20 kilonewtons. So it looks like we have only problem in the moments, but I'm calculating the moments, yes, at the nodes, but if you think about it, this element is a bilinear element, right? I did a linear interpolation to the rotations and take the first derivative of the rotation. So this element has a constant curvature. So it doesn't matter if you're at the center or if you're at the corner, it just approximates the curvature with a constant value. So the moment is constant through the length of the element. So in fact, what we are calculating here is this moment, this value is not the moment at the support, not here, but it is the moment calculated at the middle of the element. Okay, moment at the center. Why moment at the center? Because with this point load, we expect to see a linear variation in the moment. In other words, a linear variation in the curvature. But this element approximates that linear variation with a constant moment. So what we get is the moment at the center. Okay, and same thing occurs here. Again, we have constant curvature, so we are approximating the curvatures as follows with this element, with linear curvatures at each element. So this moment, the moment that we calculate here, 72 kilonewton meters, is nothing but the moment at the center of this element. So that's the main deficiency of this element. Yes, we sort of solved the locking problem. The locking problem only solved for the single curvature, and the other thing, the deficiency of this element is we only get a single moment per element, because the element has constant curvature through its surface. So in the literature, of course, there are many more elements that resolves these type of problems and improves the behavior of this type of thick plate elements.